right. Well, thank you very much. I'm going to try and look at the camera more or less because I have my notes here, my tablet here with my blackboard, and your faces over there. So yes, thank you very much for the opportunity. I really regret not being in Glasgow. I had a very minor, non-serious surgery that I was scheduled for many years actually, and I had to stay. Just the dates work out, so I couldn't really leave the country for a few weeks. So yeah, unfortunately, I cannot be there. And for some of you who attended Psycho 10, this would be kind of a more in-depth, behind-the-scenes sort of presentation on my talk there. But anyway, what I want to present today is an idea of an object that, together with my colleague and friend Andres Ortiz, who is in the audience here, we're calling chemoids. Tali's also here, so he also developed these ideas with me for the last year or so. And we are having a go at a generalized notion of compositional structures that can recover the main examples that we use every day, right? Categories, algebras, and all these kinds of things. So the structure of this talk is going to be roughly, I want to give you 3 points of motivation, and then give you a sort of a definition or working definition at the moment, and then perhaps illustrate a couple exotic examples that are not very typical, but you would agree are somewhat interesting. At least they definitely have some aspects that are not so common. So let me get rid of my floating panel here. Yeah. So first of all, let me begin with motivations. So there are basically 3 motivations. The first motivation is, or I guess the motivations are based on 3 observations. So number 1 is that label hypergraphs. Sorry. Oops, this pen is. Okay, let me change the pen. That's better. So label hypergraphs encode formal systems. So what do I mean by this? This is a very elementary observation, but nonetheless an important one, which is that if you have something like, for example, strings, or you have something like, what other? So terms, more generally, perhaps sets, and even maybe categories or polycategories, or diagrams and categories. So if you have a string, something that looks like this, A, B, C. This you can represent as some kind of graph, maybe directed if you really want to be specific about the ordering, etc. You have a term. So for example, in lambda calculus, there's some very basic expression, something that might look like this, x, y. You can always obviously draw this as labeled trees. So you could have something like lambda x, and you could have a dot here, and you could have a bracket here, and you could have an x, y here. So let me actually move this down. So sets, for example, you could have something that x, y, then something that shares y, z, w. Here's where you see the more sort of hypergraphic aspect of it. So you could have x and y, and then z and w all belong to the same hyperedge, right? And then the categories of, I don't know, some diagram maybe involving some monoidal categories. Oops. Something that might look like this. So A, B, C, maybe mapping into S, maybe mapping into X, Y. So this, I could, for example, represent the these morphisms or polymorphisms as hyperedges again. So maybe A, B, and C. These some vertices here, and then I could have a hyperedge for ABC into XY, maybe in this direction. So some kind of directed, generalized directed hyperedge, this XY, and then some other hyperedge beneath here into S, something like that. Anyway, so this is first observation. Second observation is that, so this was number one. Now, number two is that many of the algebraic or compositional structures that we normally work with have a very natural rewriting reformulation, right? So one way to summarize this is to just look at, for example, composition scatter. So let me actually write it down. So algebraic or compositional structures as rewriting. So this is again quite an old idea itself. It's nothing new, but it's something that when put together with our other motivations are sort of defining an interesting direction or giving us some interesting direction in which to push this formalism. So to illustrate this, the main example is, of course, the usual diagrammatic calculi that everyone is familiar with, for example, in categories. So if you want to see composition of morphisms in categories, for example, so let me say morphism composition. You can imagine that if you have a diagram that is labeled, that has the structure that you want for morphism composition, so labeled means that you might want some ABCs in the vertices, some F and G in your edges. So you take this as a sort of right-hand side of a rewrite rule, and this gets sent to something that is going to rewrite it, and everyone understands that here I should write something like, some name that remembers F and G, and then keep track of the labels A and C, right? So of course, all I'm doing is kind of given the diagram aspect of morphism composition in categories, but in a second you'll see how this becomes more interesting than just some kind of visual repackaging or rewriting repackaging. So another example of a rewrite that captures aspects of compositional structures is actually, for example, units. So we don't often think of units as a compositional structure itself because they are somehow just sitting in your category, but they're very natural as rewrite rules, and that's one of the aspects why labeled hypergraphs are particularly useful, is to be able to capture this kind of properties as rewrites, right? So if you have something as simple as a single object A, right, as your initial state, then you might want to think that the existence of units is basically a rewrite rule that allows us to A, right, or maybe some name. Oh, sorry, there's some comment. But I was asking about FG. Is that the ordering? Is that the question? Yeah, I mean, this is convention. Yeah, I guess you put G after F. I mean, depending on usual conventions or whatever. I don't fuss too much about those things. So this is mostly for illustration. So yeah. So in units, this is a way to represent it. Again, it sounds a bit kind of pedantic to say that this is a rewrite rule, but you will see that it actually works out. And to give another example that is not just the basic definition of the category, for example, something like an operad. So operads will have actually a tower of rewrite rules where operad composition will have to proceed in different orders. Just to give an example, I can write a quite small one, something like this for example. So if I label everything A and B, and I label the vertices, for example, 1, 2, and then 3, 4, 5, 6, 7, 8. Composition here. So now this is again some label a hypergraph, and then the rewriting, as you all know, is that you get a single term out, right? So A and B go into, so you know, the vertex 2 is left there, very much like in the composition of morphisms up there, and what you end up is with a single edge that has 3, 4, 5, 6, 7, 8. So it has 3, 4, 5, 6, 7, 8, and it goes into 1, right? It goes into 1, so something like that. That's 3, 4, 5, 6, 7, 8, and you call that A, B, or whatever, right? So again, it looks just like rewriting, like reformulating basic diagrams, but because of observation 3, we will see that this is actually more interesting than simple, you know, reformulation or taking a more diagrammatic perspective on categorical structures. So the third observation is that many of the axioms that normally go with these compositional structures can be characterized and can be captured in a very natural and simple manner in terms of rewriting properties, right? And for this, I want to work through a couple examples to you know, make you walk through the same kind of ideas that I originally encountered when I was investigating these kinds of systems, to see if you agree that there seems to be a pattern that deserves sort of proper attention and deserves to be brought to the fore and to be discussed in sort of as a main focus of interest, right? So let me well, the first one that is the most obvious one is associativity, which was actually the motivation for me to get into this topic and to begin with, to study higher forms of associativity in algebras. So associativity. For this, we basically take this kind of diagram. We take the morphism composition, and we're gonna present an initial state to basically perform our rewrite rules on it, right? So actually, I'm gonna make things undirected because the illustration is equivalent for this. So if I do F, G, H, I'm gonna do A, B, C, D. I mean, I'm gonna drop labels in a second. Basically, what you can see is that if you take this as your initial state and say you're in a category, so you have both units and morphism composition to apply, you can, you are in a semi-category, so you only have morphism composition to apply. Then there's two ways in which you can apply that rule. I mean, this is very elementary, going back to learning category theory for the first time. So you can either make so I'll make it highlight this. So you can take this pattern, so the rewrite happens in this one, or you can take this pattern, so the rewrite happens in that one. So this is rewriting that way, and this is rewriting that way. And so the result is some edge here and some edge here, and then the rest remains. So this edge is AC, so it goes to D. This AC goes to D, and this is A that goes to B and goes to D. Now again, you can rewrite these two to obtain basically two edges between A and D. That's kind of the bottom line. So now you get two edges between A and D. So if you actually keep track of the naming labels of the morphisms, or the edges in this case, you would see that if you had a name that kept track of F, G here, or the other way around, if you use the other convention, and H here, and you use F here and GH here, you end up with two different names. You end up with something that, I mean, you're using a sort of a tuple of symbols to represent to label the edges. So on the top one, you end up with something that looks like FGH, and the bottom one, you end up with something that looks FGH, right? So the idea is that this rewrite perspective kind of discovers the axiom of associativity, kind of discovers that you should somehow make these two expressions equivalent, because you started with a simple graph and you ended up with a non-simple graph. You ended up with two edges of the same graph type in the diagram. So of course I didn't draw them, but the other vertices are still dangling around here. It's not that they are destroyed or something. And there, B is there and C is here, and they are at the end also here. So B is here and C is over there, right? So you can think of this as just a rewrite process on the same set of vertices, and then you're operating on those. So the insight here is that there seems to be a clear correlation between the typical algebraic axiom of associativity, written in this way, and some kind of vague equivalence between this and some kind of confluence. Also, the fact that these two motifs, these two patterns that you were rewriting, were somehow overlapping. And obviously there's something to do with the labeling. The labeling is kind of what made you write that axioms in the first place. Okay, so this is one of the main motivating examples. Let's see a comment here. Yeah, no, it's just on the tablet. So okay, so this is a very well understood example. Now the other one that kind of justifies and shows a little bit a hint of the generality of this approach is, for example, units, right? So I claim that units are can be encoded in this nice rewrite language. And the point is, okay, what is the advantage of that? Well, the advantage is that with a very similar general principle, you obtain the algebraic axiom of units. So for neutrality, which is the kind of the property, the algebraic or compositional property of units, you have the following. So now imagine that you are in what I might call a unar, which is just like a category but without composition. Sorry, that you are in a unar, so you can only rewrite units, but then you also have composition, so you are actually in a category, and you start with a state that looks like this. So A, B, and just a labeled edge. So if we have both composition and unit rewrite rules, we can only apply the unit rewrite rule to this diagram, because we can basically only find the left-hand side of the unit rewrite rule, because there's only one edge in our initial state. But we have two vertices, so we can apply that rule to each of the vertices, to either of the vertices. So just by choosing one, for example, A, we can rewrite this and write. Maybe write in red. Here's the unit and everything else, and perhaps the duplicated A, if you like. And then you have A, you have F, you have B. So this is very elementary. This is really, but I'm trying to build up a sort of a philosophy here. And then of course now we have two edges, and we can apply the composition rule. So for that, you have red, you have A here, and you have B here. And you basically, so you have F, and you have the newly created 1A F, for example, right? So you can imagine that A is still floating there, if you like. But because we are using labeled hypergraphs, you can basically forget about those, because that's just redundant information. You can always throw in more objects or vertices that are labeled redundantly, and they don't add any information. So the point is that, again, we find ourselves in the same situation where we have two edges of the same sort of graph type in this context that are labeled differently. And so again, just a rewrite phenomenon, keeping track of labels, has kind of rediscovered the compositional or algebraic axiom of units, right? Because all I want to say is that 1AF equals F, right? Which is the left neutrality property of units, right? And similarly, if I applied, so you could do the same thing by applying the unit rule 2B in this diagram, right? And you will find those. So that's quite neat to have this rewrite reformulation of both associativity and units, which are essentially the axioms of a category, purely in terms of rewriting systems of label hypergraphs. And then, of course, many of you might have heard from my talk in Psycho, there is a more exotic example of semi-heaps. So semi-heaps are these ternary algebras that have a quasi-associative behavior. So I will present first what a semi-heap is. It's basically just a set with a ternary operation, and it satisfies the following property. So you do the triple product, right? A triple operation ABC, then DE. You do it twice, and what you can do is you can move the brackets around, right? So I can have some bracket in the middle, and then I can have some bracket to the left, to the right, this side. So the left and rightmost cases are exactly as you would expect from associativity. So C, D, E. No surprises there, but the middle one has a little twist. So A and E remain the same, but then C stays in the middle, but D and B swap roles, right? So this is what's called a semi-heap. They were developed in the 40s and 50s in the 20th century. Some literature exists on them, not much, but they are some other kind of compositional structure. Of course, you can make them into sort of partially defined. So you have like semi-heapoids and heapoids and things like that. They're very closely related to groupoids, as you can imagine, because if you give me a group G with a dot operation, you can always define a ternary operation ABC. Sorry, you can always define ABC sub G by making this, right? And so with that particular form, you can see very intuitively that you're going to get associativity on the right and on the left, but in the middle, because you have inversion, you're gonna get this twist behavior that you're flipping B and D, right? So semi-heapoids, by the way, are essentially affine versions of Dagger categories. So in any Dagger category, you have the home set of your Dagger categories have the structure of a semi-heap precisely. So as partially defined algebras, semi-heapoids are basically kind of affine versions of Dagger categories. I say affine because in these algebras, you don't assume any existence of units or anything like units. When you do, the story becomes a little bit more complicated. But quite generally, intuitively, you can think of semi-heapoids as some kind of affine version of Dagger categories. So why am I bringing this up? Well, the reason is that these two diagrams seem extremely, just some kind of notes taking when you're learning category theory for the first time. But the reason why I had to go back to looking at diagrams in category theory, like I was first learning them, was that I was trying to understand things like this. I was trying to understand the higher associativity like this, semi-heaps or other kinds of algebras. And I realized that actually this perspective of compositional structures as rewriting gave me a quite straightforward path into getting them. And kind of one of our main discoveries so far, and I say discovery because it was something that is not really known, not because it's like a great breakthrough, was that this particular structure can be recovered with a very simple and intuitive rewrite system. And so there's actually two ways of doing this. So you can either use directed to graphs, just digraphs, or actually undirected if you want. You can also do it directed and you will still see the pattern. Undirected 3 graphs. Actually, you can do it with any order of graphs, but with a specific order constraint. So the way it works is as follows. So you have again, these are just labeled hypergraph rewrite systems, right? So these are just ways in which you're going to take some state hypergraph and you're going to apply some motif detection or motif pattern matching, and you're going to rewrite it in some deterministic way. So the idea is the pattern that you're going to match for the two graph case has this structure. So three vertices, so three edges, apologies, and they are directed exactly in this pattern, right? So call them ABC if you want. So they are connected in this non-flowing pattern, right? It's non-circulatory pattern, and they get rewritten. So this is the rule input, and the output is, again, you keep track of the vertices, they don't disappear. It's just rewriting, and you give a single directed edge, and maybe you call it ABC with a tuple, right? So that's one way. The other way is, and it's quite visually clear that these two are equivalent in some sense, is to have edges. So now we introduce ternary edges in this particular topology, which you will not be surprised that I like to call a fish. Right, so these are two different triangles, and these are vertices. Right, so you take this as an initial state. You might want to, call them ABC, the triangles. And then this gets rewritten to a single triangle. Maybe write like a long triangle here. And you call that ABC again. So what's important, and again, the three other vertices are dangling around there. What's important here is that the naming convention is taken ABC in a sequence because it's a graph and there's no ambiguity there. And in the fish, you name ABC in a sequence, again, by matching the topology of the graph. So you can always, I mean, the topology of the fish actually allows you to identify what's a tail, what's a body, and what's a head, right? Just by kind of the anatomy of the hypergraph. And so you can just arbitrarily say, well, I'm going to order tail to head, and I'm going to go ABC in that sequential order, right? So there's something that in the case of a basic category was very redundant. Is you say, well, I have a sequence of morphisms because they form a digraph, so I'm going to use a sequence of symbols to represent them. When you go into this, I mean, in the case of the directed graphs here, again, you have a sequence of edges, so no much ambiguity. But when you get into these three edges, these order three edges, you need to get some different kind of criterion to. So in this particular example, it's quite easy to do because you still have some kind of sequence of ternary edges, right? I mean, the fish is kind of longitudinal; it has that sequentiality built into it. But still, you assign the labeling in terms of the topology, in terms of the anatomy, so to speak, of the diagram. Okay, so what's the punchline here? Well, the punchline is that when you regard a compositional structure on labeled hypergraphs like this, then you can actually find this axiom. And I think it's kind of intuitive just from the look of it, that you have this kind of twist in the middle. You have two triangles that kind of go in the same direction, one triangle that goes in the opposite direction. So, but we can see this very explicitly, and I don't want to spend too much time drawing the diagram because I'm sure many of you have seen it before. So if you take a diagram with 5 triangles like this, and again, this is all labeled ABC, and there's all indices everywhere that are labeled A, B, C, D, E. You can spot fish structures here in several ways. There's actually 3 ways. So there is a fish at the left, right, in the left position. There's a fish in the right position, and then there's a fish in the middle position, but it's just swimming in the opposite direction, right? So there's a fish here in the middle. And so I'm using this notation. So this is on the left, this is in the middle, and this is on the right. So I have something like this. So these are the three fish occurrences in this diagram. And of course, when you rewrite according to this rule, what you get is again 3 fishes, right? You get this red fish becomes just a triangle. This red fish becomes just a triangle, but now in this direction, and now that fish becomes just a triangle. So if I write the other triangles, I get this 3 states. And of course, all these, again, rewrite as, because they are fish, they rewrite to a single triangle in the end. I mean, each of them give you a different triangle. Now, the labeling of these are different, right? So the labeling here, I have A, B, C in the red triangle. I have B, so I have B, C, D in the triangle, but the triangle is oriented in the other direction. And because my tuple keeps track of the anatomy, tail, body, mouth, or tail, body, head, I should reverse the order, right? So I do D, C, B, because the anatomy is what defines the order of the tuple. And this one is, again, C, D, E. And so when I rewrite to the end, where I get this confluent final state, I get 3 different expressions for the same type of edge, right? Because it's an edge occurring in, I mean, if I highlight with these colors, just first to summarize, these vertices here, there are sort of dangling vertices in the middle, but those 3 vertices at the start are precisely these 3 vertices at the end, right? So I have 3 ways of finding such edges between those 3 vertices, and they have 3 different names, and the 3 different names are precisely these, right? So that's kind of another application of this rewrite perspective. And so by the way, something that looks like this could be called an undirected heapoid or undirected semi-heapoid, I guess. So if you have something like a category where you have your objects, which are the vertices, and you have your morphisms, which in this case are ternary, so you have something that looks like a category but with ternary morphisms. If you impose this particular composition rule, you end up with something that has been known for some time, which is called a semi-heapoid, right? Which is this sort of partially defined structure. You can only compose when you actually match the proper domains, so to speak, right? So you actually find the pattern of a fish. You can make those 3 morphisms into a single morphism. Again, if you're familiar with Dagger categories, it is actually very simple to see that one way to find semi-heapoids in that context is that whenever you have a structure like this in your category, so F, G, H between some objects, you can just define the product. Sorry. What I mean is you want this non-circulatory diagram, like here for the semi-heapoid, and if you're in a Dagger category, you can turn this into a single morphism from beginning to end, right? Simply by applying the dagger to the G so that it flips, right? So you get now something that is circulatory, F, G, dagger, H, and now you can just compose, right? So the final thing looks like F compose G, dagger, compose H. So any Dagger category gives you an example of a semi-heapoid. And again, semi-heapoids are kind of the affine version of this. So you forget about units, you get this kind of displaced, non-privileged way of composing stuff. But they're somehow just lurking in very familiar structures like Dagger categories. So anyway, so these are the 3 motivations, right? So it's what led me to consider the possibility of defining something that is more general than the usual compositional structures that at least I knew about, categories, operads, and so on, and to go into this rewrite philosophy that allows us to try and have a. So the problem was to have a handle on completely general associativity-like properties, right? And well, one of the surprises was that things that don't look like associativity, like unit neutrality, also fit the same pattern. And then, of course, the good surprise or the nice realization was that algebras that we were trying to understand, like these semi-heaps, fit perfectly the picture once you're, clever enough to find your patterns. So you had to be clever enough to find this non-circulatory pattern, which, by the way, was first used in semi-group theory and semi-groupoid theory in the early 2000s. but no connection was made to some kind of generalization of categories in this way. So if people are curious, there's actually some traces of attempts to generalize categories in this sense, but they never kind of crystallized. They never consolidated some of the early suggestions. And so these three observations were the motivation to define what we are calling chemoids. So actually, there's a comment here. Right. So Jax is asking, the rewrite used in neutrality is different than some of the others in that it's expansive instead of contracted. So in principle, the nature of the rewrite rule is somewhat irrelevant, right? I mean, that's kind of the philosophy that I want to put forward. The nature of the precise behavior of the rewrite rule, it's not so important. What's important is that you end up with diagrams that can be compared, right? So of course, we've seen this kind of reductive rewrite rules, which are the usual algebraic rewrite rules, right? The unit rewrite rule is somehow, it somehow creates stuff on your diagrams, right? Obviously, the interesting aspect of this phenomenon this overlapping confluence kind of phenomenon is precisely that matter of do our diagrams grow up and explode to infinity or not, just by doing the rewrites, right? And so the idea is that we don't want them to blow up and to grow out to infinity and become arbitrarily large. I mean, it's not that there's a problem if they did that. I mean, formally, I guess there's no issue. But when you're trying to think of your diagrammatic calculi as some kind of automaton that is operating this rewrite, it's not really an automaton because there's still sort of equivalence relations in the background and so on. But you want to make sure that the diagrams represent what you're conceptually trying to capture. So by that I mean this property here that I highlighted before, or this property here, can actually be spotted in a much simpler setting, which is to say, well, if you have a single object, you can create the unit on that object, and then you can keep on going, right? So you keep on going, and then you do. So now I have units like this, but then I realize that these are all the same object. Everything is labeled A, right? So just by applying the same rules repeatedly, you actually found this kind of situation where you had, maybe this is called 1 and this is one prime A, because it's part of a process that is distinguishable, right? The first iteration, second iteration, etc. And that's exactly what you want to impose. You want to impose that these two things are actually the same thing, right? So yeah, thanks for the question, Jackson. That's actually a good way to bring it down even to the most basic level, that you want to impose some aspect of non-multiplicity, right? That things don't blow up just by rewriting subsequently. That's kind of the balance that we want to strike, by the way, before I move to the second and last part of the talk. The balance that we want to strike in this theory is we don't want to be completely algebraic and completely axiomatic, like category theory normally is, or algebra, more conventional mathematics is, but we also don't want to be just like automata theory and think that this is just some computational system that has some life of its own and just that's its thing, and we are kind of studying it like kind of zoologists, right? Computational zoologists. We want to live somewhere in between, where we have, we leave the system to rewrite, and we have this rewrite multi-way graphs that give different paths of operations, but we also want to have some kind of control over the structures that are possible, and we do that by having some kind of quotienting procedure by the labeling, right? And this is exactly what I mean by this non-multiplicity principle, right? The fact that you want to somehow capture the fact that you ended up with 3 triangles here in the fish thing, you ended up with several units or arbitrary number of units just by applying the unit rewrite rule, or you ended up with, if you make a longer, by the way, there's nothing special about 3 morphisms in this diagram. I could make an arbitrarily long chain, and you would get a rewrite system that is just bigger, and so you would end up with more copies of the same type of edge at the end. right? And what you want is that they are all the same, and basically what that amounts to is that you can place your brackets and you can displace it in any position, right? So there is some degree of multiplicity that you want to keep controlled, right? And that's kind of the punchline of what we want to define. So as a proposed definition, and I will try to be quick to give you a definition and then actually present, where am I at here? So the definition is what you can expect. I mean, there's nothing too fancy going on here. So all we do is we use this chemical language because I find it very, very useful. And actually, you saw it in a recent paper. So some people are, getting this fashion of chemistry in abstract mathematics, which I think is very useful. So I use atoms to signify the element, the sort of primitive elements. Think objects and categories. Then you have bonds, which are some kind of data structure on atoms. So I'm being deliberately vague there. So think morphisms. So morphisms would correspond to traditional category morphisms correspond to tuples of two tuples of atoms. Then you have molecules, which are hypergraphs from bonds. So essentially each bond is a hyperedge, and a molecule is a collection of hyperedges. Right? So think in category theory just diagrams. And then finally you have reactions, which are the rewrite rules. So these are, axioms, operations, etc., right? In conventional categories. So these four ingredients. Sorry, there's a comment. Is that a question? No, sorry, previous comment. So these four ingredients give you basically the groundwork to do category theory, or to do this generalized version of category theory, without the behavior that associativity, for example, captures, or that the neutrality of units captures. And so to all this, you have to add some kind of, because so far that would basically just be a computational system. That would be some kind of automaton. You give some possible ingredients of labeled hypergraphs, and that's specifying some symbols. Your atoms are some basic symbols, and then you have some. Maybe you want to say I'm only going to consider undirected hypergraphs of order 17 or whatever, and then you define your universe of possible objects, and then you choose a rewrite rule, and you get all these rewrite systems there. And so that's a very much a sort of an automaton, kind of a computational zoologist point of view. But we want to do something else. We want to take that as kind of, that's what's going on in the background, but we want to extract something that is a bit more mathematical out of that sort of computational world. And for that, we need to enforce this property that when you get this overlapping confluence, you somehow quotient and you say this labeling was redundant somehow, and I'm reducing it. So I'm giving that just a name because there's this chemical analogy. I will call it the principle of molecular integrity. But you could also call it diagrammatic simplicity. Simplicity. And basically what it says is you have all the possible ways of rewriting whatever state, which is a diagram that you're going to work with. And then if you spot an instance in which some hypergraph subdiagram of that diagram, which was simple, which you can always choose. Simplicity, by the way, means that you don't have more than one edge per type. Type here means that edges are not just a collection of vertices, but they also have some data structure on them. So there might be cycles of vertices, or there might be tuples of vertices, or bags, completely unordered collections of vertices. So when you have a labeled hypergraph with some sub hypergraph that is simple, and you apply rewrite rules, and you find some instance of non-simple hypergraphs that the labeling allows you to actually distinguish, then you should impose some quotienting on your sets. So by the way, when I say atoms, bonds, and molecules here, these are really, if you want to have a more traditional mathematical definition of this structure, these are sets, right? So it's maybe you define the atoms as a class, whatever, large class, whatever. And then bonds, you might want to say, well, for each possible data structure made out of atoms, you want to build a set, right? So that we have the direct analogy with home sets in categories. And the idea is that this principle of molecular integrity is going to either be fairly trivial when just expressed as explicit rewrite properties of your labeled hypergraphs. There might be just some general confluence property, or some kind of the basic fact that your diagrams are unique and something like that. That doesn't carry a lot of information. But if you start labeling things on your home sets, on your bond sets in this case, then you're going to find non-trivial relations like we did before, right? I mean, in some sense, what I'm trying to say here is that when I draw this diagram of 5 triangles, or I draw this diagram of 3 morphisms for the associativity property, these diagrams are unique. Right? There's nothing multiple about FGH in this particular topology, right? It is when I parse is when I digest the diagram by a rewrite, so I submerge it in the solution and it starts to react, and that I want to keep track about the causality of those reactions. So my labels are sort of attaching to each of the edges that are getting rewritten, that I actually am able to spot something like associativity, and then I need to say something non-trivial. So that's kind of why I'm calling the principle of molecular integrity or simplicity a principle, and I'm not just saying, oh yeah, this is the technical underline. This is it. That's how you implement it. Because it really depends on if you want this to be some kind of computational background to do diagrammatic calculus, or you want this to be a foundational schema or have a collection of foundational schema based on this to then do category theory or set theory or whatever you want, or monoid theory, or all these things, right? It really depends on what you want. My personal view is that there's a lot to learn just by considering them as general rewrite systems and just trying out different motifs and different rewrite rules that you can interpret in some natural way. And obviously we understand that the rewrite rule of categories, right? A rewrite rule that takes 2 edges and rewrites 1, it's very strongly connected to the notion of path. Right, it's very strongly connected to the notion of walking around in a graph and basically the groupoid of paths and things like that. I mean, it's a very strongly physical, in a sense, strongly conceptually powerful thing to do. Now, what does a fish do? What does other topologies do? This is much more of an open question, but we're trying to present a kind of framework that allows quite a systematic approach to all these potentially very, very vast questions. So I would stop it there, although I do want to keep a note that I have this example of bag algebras as a bit of a more exotic, very simple but somewhat exotic application of this kind of approach, because so far maybe perhaps semi-heapoids are a bit less exotic, although you can see them in some kind of way as Dagger categories. So these are all kind of familiar and well known. Bag algebras are a good example of a very simple structure that kind of resists typical treatment in usual algebra, in usual model theory, if you like. But however, that has a very natural interpretation in this chemoid setting. So what I would do is I will open it for questions and comments, and if we have some more time, I'll give you the rundown of bag algebras in 5 minutes. Thank you very much.